Alrighty then. We all know what time it is. We need to do our summoning chant.
Almighty protector of the sun and sky, I beg of thee, please heed my cry. Transform thyself from orb of light and bring me victory in this fight. I beseech thee, grace our humble game, but first I shall
call out thy name. The winged dragon. The Spherical God Cow. Yes, that's what we're talking about today. Hey guys, what's going on? Memes here, yes. If you couldn't tell from the name of the stream, it's a wee bit of a joke. But what happens if you take certain concepts seriously, occasionally you'll get certain coincidences. Does it mean anything? I don't know. It was something I wasn't expected, so we're going to explore it today. And this is something we had touched upon a little bit on Friday before Paradigm Drift, just because I basically had just done, what was it? I think I'd finished the Sean Carroll video, and his biggest ideas, one of the very first things he does is he talks about the concept of the spherical cow. Okay. Just to reiterate, the concept of the spherical cow within physics is an idealized scenario. Basically, we realize that if we're trying to do all this stuff in reality, there's all this different stuff that we try to keep track of. You're supposed to account, I believe, I learned it was the infinite amount of uncontrollable variables, and you try to control for the variables the best you can. AKA, you try to conceptualize an ideal situation, because for any of you all that have ever seen an actual cow, it's not a sphere. It's a cow. But it's basically taking that concept of, what if we imagine it as an actual perfect sphere? And apparently, utilizing that concept within the realm of physics is useful for at least some different thought experiments to see what might be going on. Okay, so yes, and that also, Yu-Gi-Oh! Intro was just so I could use this thing that I got at FanFest from, I got the 3 Egyptian god cards in little plaques there. So we got our little winged dragon of Ra with a little inscription and stuff down there. It's not actually necessary. Let me move it onto this side. So there we go. All right. Actually, I'm just going to put this on the ground because I know it's going to fall. There we go. All right. So why am I talking about this, and why the heck is there something where it's like the Higgs, that says cow, even though there's a little bit of lighting there. Yes, my poorly drawn Higgs cow, because to summarize what the heck we're talking about, what do? I spend a lot of time going down Wolfram holes, basically abusing the heck out of probably one of the largest, if not the largest, computationally freely available databases of stuff and things in human existence. I think the last time I heard Professor Wolfram say something on this, he's like, Wolfram Alpha literally has over 10,000 different units. A bunch of them are depreciated and or not often used. That's kind of a shame, because certain units, if they were more freely used, perhaps they might be telling us something about what's going on in reality. Again, I'm very biased. And again, I'm not a PhD in physics or mathematics or anything. I am a dude on the internet that's interested in different stuff like a lot of you all out there. So let me just recaffeinate real. But we're going to be talking about the whole concept of what happens if you take the idea of a spherical cow seriously. Like, literally. And let's go over kind of how we kind of came to this. So I'm saying the Higgs cow, what the heck is this thing over here? Long story short, I was setting up the board for Paradigm Drift on Friday in case I got selected. I was not selected, that's fine. I've already been on like 3 times. I'm probably one of the almost a regular without actually being a regular, but this is supposed to be representing the mass energy of the Higgs if we literally were to divide it by a sphere. Okay. It's literally 4 pi r cubed. Just a standard thing that we learn for a sphere. 4/3 pi r cubed, because we're assuming 3 dimensions here, so 4/3 pi r cubed. And you're like, and so what are you using for your r? What are you using for your radius? Well, if something happens to have mass, there's a conversion. There's a quick calculation you can do to get an associated Compton wavelength for it. Okay, does that actually mean that's the radius of the particle? I don't know. But what ended up happening is you do that and you just use the Compton radius, and then when you plug it in, you get a ginormous number. This was supposed to be a poorly drawn Einstein here with crazy hair. He's holding a K or kappa symbol there. Because what happens if you multiply this Spherical God Cow by the Einstein C4, speed of light raised to the 4th, kappa convention, you get 1 over meter squared. Or maybe like 0.99 or 0.98 meters squared. That seems a little strange. Long story short, this comes out to be about the magnitude of this, and this is the factor that you multiply by the vacuum energy density of universe according to Planck or whatever, and depending on the data set, it might change, go up a little bit or whatnot. But this at least seems to have pretty good agreement with at least the Planck survey for the cosmic microwave background. And if you're taking more of the, I believe, the local supernova data, as soon as you get out the further levels, maybe there's some weird stuff going on. Maybe there's something we haven't really accounted for in our models. Maybe dark energy isn't even a thing. Maybe it's changing. Maybe it's not a constant. That seems to be a continuing thing. We have all these things like, well, this is a constant. Well, it's a cosmological constant, but it seems to change depending on our data set. Maybe it's just changing in general. I don't know. Or the fine structure constant. Well, it seems to couple and run with energy. What does that mean? It's at low energy. It seems to be about strength of about 1 over 137-ish. Yeah, you get higher energy, and all of a sudden it's like 100 over 1 over 128-ish strength or something like that. What's going on there? I have no idea. Something, higher order terms, blah, 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 blah. Again, I'm not a quantum mechanic. Welcome, nerdy. Yes, we're talking about the Spherical God Cow, and okay, I'm just going to show the picture, just because this was totally from ChatGPT, and then I just I tweaked it a little bit. So let's where are we? All right, our friend over here. We don't need to share any more Yu-Gi-Oh chants or anything. It's all right. It's all right. It was totally worth it. All right, so what we got here? All right, the Spherical God Cow. What the heck is this crazy amalgamation? How many sides does the cow have? Is the inside the same? Those are wonderful questions, Dirty. I have no idea. All I did was, please create a 16:9 image, taking the physics concept of the Spherical Cow and combine it with an anime aura like Ultra Instinct. And it basically gave me generally what I was looking for. So the whole reason and the name for this is we're taking the concept of the Spherical Cow, we're applying it to what some refer to as the God particle, even though that's not really correct. It was mostly done by to sell more books back in the day, and apparently it worked, and then the name just kind of stuck, and people will say it's the God particle. I don't know about that. It was basically the last observational piece of evidence required for the standard model to be complete as we know it here. Now, is the standard model completely done? No, we haven't. We don't have a grand unified theory. I mean, a lot of times this is something that I heard from Professor Keating is we're putting the toe in front of the gut. So basically people will say a theory of everything. Okay, what does that mean? You're supposed to explain all the concepts, the stuff and things going on within the physical universe, but if you take it literally, you're trying to explain everything. Are you accounting for consciousness with that? Is consciousness built in? Am I conscious? I don't know. I feel like I operate like a lame language model a lot of the time. I'm just predicting next word that makes most sense there, and it's that's not what we're here to talk about here. So basically, I was listening to a Sean Carroll video and stuff, and because a lot of stuff that I was initially listening to that I had no idea what he's talking about, the algorithm brings it up, and then I'm re-listening, and I'm like, oh, I actually kind of understand what he's talking about now. And then you go through, like, just browsing a Wikipedia article, different archive articles and stuff, and then you'll see something where it's like, well, it's people have proposed different ways for, like, maybe the Higgs to be done, something with early inflatons or inflation or something like that. I look at that and I'm like, well, people have obviously studied this deeply and everything, so why would I even look? Eventually, I just got kind of curious. I'm like, well, if the Higgs is an elementary scalar field, or it is something along the lines I've heard, the only elementary scalar field that we have evidence that it actually exists. Okay, a lot of smart folks out there, let me assume this was true. If this is the Higgs condensate or whatever, like spreading and filling up all of reality as we know it, is there anything else that seems to spread up all of reality as we know it? You might occasionally see something on Twitter or whatnot. People post something of like these quantum fluctuations. What is it? They just show a box with like these little blobs kind of like moving around in this crazy fashion. I'm like, well, it's a storm of virtual particles. These things that don't exist. There's energy. Long story short is apparently the vacuum, quote unquote, it isn't actually empty. So it's kind of, I don't know, I'm part Irish, so I think I can say it. So it's like No True Irishman, where it's like, it's most Irish folk, I don't know. I don't know. So basically, is it a true vacuum or there's stuff there? So there does seem to be a measured energy density. It's like 10 to the minus 10 joules per cubic meter. A really small number. Okay. Now, if you do the naive thing, for the Higgs, what you can do is, let me stop sharing that. All right. Let's just go over here. Oh, I closed all my tabs. It's okay. So let's just bring this up here. Let's see. But oh yeah, yeah, crypto. My email should be over there. It's literally the memes of destruction at gmail.com. Should be on the YouTube tab and stuff as well. But it's the Super Saiyan cow. I was going for Ultra Instinct just because it's at least within the realms of anime and stuff that was within, I think, the gods arc or whatever, because all the gods and stuff like that got together and had all the mortals fighting each other because, well, that's obviously what gods would do, and seems to be very akin to a lot of ancient Greek tales, if you would. But welcome, some person. Oh, let's see. Valence shell phase shift fusion mode. Oh, that would be really cool. That's the thing. I just look at stuff. I can speculate and speculate and speculate, but it's kind of like, how far off of the farm, so to speak, am I going from what we know and what other folks have said? Now, again, I ain't no Einstein or anything like that. I'm just a crazy person on the internet that occasionally gets a little obsessive about things. That Thad taught me how to use Wolfram Alpha several years back. It took so much time for somebody like me that just math was always scary and everything. It's like, wait, it does most of the math for me. Oh, and at least as a first pass, because if you actually want to look at what's going on, you're going to want the most precise measurements and stuff like that. And look at the data and stuff like that. Get as many significant digits as you can to see if there's a pattern there. Because a lot of times it's just a coincidence. Was it Sean Carroll at one point, he had said, there was a conference on modified Newtonian dynamics. And apparently Professor Maldacena, it's from the holography fame, so to speak, the whole ADS CFT correspondence. It's, I think, the most cited paper in physics as we know it. He's sitting next to Sean Carroll, and he's like, well, it matches? It's like, well, it must be right. And then Professor Carroll just casually turns, he's like, maybe, or maybe it's just a coincidence. So I'll leave that. I'm not going to argue about that today. I'm just going to look at the very base calculation that I did just following my thought. And again, I call it this because one, it literally is the concept of the spherical cow, and two, I'm like, I looked, or at least I did a cursory Google search, and I found one paper on the archive that I think they noticed the same thing. It's I believe they're a string theorist, and they're coming at it from more of a string field theory network, but they didn't actually have calculations and stuff. So I know some folks love to rag on string theory or something. I don't care where a good idea comes from. If it came from the string theoretic landscape, great. But they were looking at a geometric mean, and I didn't find anybody that just came to literally just the most noob reaction. So let's not dilly-dally anymore. Let's share this with the class. There you go. Window over here. Let's go to Wolfram. All right. So I'm not even going to put in any of my conjecture ratios or stuff like that, because it's like, yeah, I could say, oh, it's the square root magnitude of h bar scaled by the Planck mass, and you get something that agrees pretty good with recent measurements. I don't know if that's right or not. Who knows? So let's just do the most naive thing. So we'll just do the Higgs mass. Okay, it's going to give us a number here. Okay, really small number, but we want its energy, because if you want to compare it to the vacuum, energy, we want the same units. So we're going to take its mass energy. Okay, got the mass energy of the Higgs. So basically 125 GeV. It's right around there. It looks to be probably a little bit over that. I think Wolfram has it as like 125.18 when you actually go to the particle. But all right, so we got the mass energy of the Higgs. Now, let's literally invoke our spherical cow. What do? We're going to divide it by 4/3 pi. And then we're going to multiply it by r squared. Excuse me, r cubed, because we're doing a volume. Apologies. So 4/3 pi. But what are we going to use for its r? Well, the Higgs boson, it's got an associated Compton wavelength. Let's just do the naive thing. So Higgs, Compton, wavelength. All right, we've got that. We need to cube that term to get a volume, because that's just a length. So length squared is an area. Length cubed, we get a cube. We get a volume, and we're just trying to convert it into a sphere. Okay. So we take all that. We hit enter. Go Wolfram Alpha. Does the computation for us. All right. So you get this ginormous number here. I'm like, I have no idea what that means. It's a bunch of gobbledygook. It's about 5 times 10 to the 42 kilograms divided by meters per second. I have no idea. That's an energy density, because normally mass times c squared. C squared is meters divided by seconds. But if you're trying to find an energy density, we divide it by a volume. So the two things of meters, or the two factors of length in the numerator, cancel out. And since you had 3 factors of length, one ends up going in the denominator. So that's why it's meters there. Because if we multiply that by volume, we would just get an energy. I'm sorry, that's kind of mathy, but again, no idea what that number means. But let's compare it to because like let's just click on this real quick. So it's basically a pressure or energy density, because it's giving us those units. Okay. So as we can see right here, it's very large, like about 10 to the 51, almost 10 to the 52 times the actual universe vacuum energy density. What could it actually mean? Let's go back. So let's literally just divide this into the universe vacuum energy density. All right. Our little protective brackets on. There we go. Go Wolfram Alpha. It does the maths for us. And again, keep in mind how much data you're going into there, because occasionally If it spins off and it gives you like 40 digits, you only put in 3 digits accuracy. It's just rounding. It's just going on, and understand where the data is and everything, because otherwise that might lead you astray. All right. So we take the vacuum energy density of the universe, and again, depending on the calculation you have, this has pretty good agreement with at least the cosmic microwave background and lower and more closer phenomena that we believe we've measured. Okay. So the universe vacuum energy density, the energy density of the vacuum itself, if we divide this, I don't know, spherical God Cow into it, what do we get? We get 1.1 times 10 to the minus 52. That's the little thing I put on our little spherical God Cow thing. Why did I put that there? Well, we checked to see at least the first order, or at least I'll just put it. Cosmological constant. Let's take a look. The cosmological constant, it's this here, it's that lambda thingy. Here's the definition. It's that 8 pi big G over the vacuum energy density divided by c to the 4. That's just 8 pi divided by the Planck force. This is something that Dr. Salvatore Pais has brought up as an interesting thing a number of times. So I'm like, okay, what's its value? 1.1 times 10 to the minus 52. Inverse meters. So reciprocal square meters. So basically, it's like something is inverting or stretching out in a way. Wait a second. 1.1 times 10 to the minus 52. 1.1 times 10 to the minus 52. WTF, mate? That's a very interesting coincidence. Again, it doesn't have units there, but I'm like, what the heck is going on? That's why. Okay, my first thought is, number one, I made a mistake. Number two, this is just a very simple thing that, well, if every particle has an associated Compton wavelength, maybe this is just a general thing, because kind of like when I was playing around with like H bar, you can kind of, at least I would claim naively that if you have something like the proton mass and times the speed of light times the proton's actual radius with maybe a factor of 4 or something like that, you get out. Basically, you can calculate Planck's reduced constant, h bar, and actually have some prediction power for extra different variables. And okay, so I'm just thinking, okay, this has just got to be, it shouldn't matter there, because, well, if you put a different mass in there, well, the Compton wavelength would be, so I figured it would be the same. It doesn't seem to be the same for the other particles. Like the electron, I think, is far too small. I tried the Higgs, the vacuum expectation value of the Higgs. It's like 246.22-ish giga-electron volts and everything like that. It's like, okay, that's very weird. But long story short is, let's duplicate this. So we're gonna duplicate this. And let's just try. And again, maybe I just made an error. Let's see. Let's take electron mass. Do the same thing. Let's change this to the electron Compton wavelength. Okay, 4 times 10 to the minus 31. We did the same factor in there. All right, let's... The proton, I think, was the closest thing I could find. Okay, it's like, yeah, 3 times 10 to the minus 44. How about this? Let's just put in the proton radius. So don't not do its Compton wavelength. Radius. Okay, 9 times 10 to the minus 45. How about classical? classical proton radius, just assuming it's a little ball of charge. Okay, yeah, it gets within about 2 magnitudes there. Oh, let's go back to the electron. Let's do electron. Hold on. Classical. Electron radius. Okay, 6 times 10 to the 40. Let's do the Bohr radius. And again, depending on what, yeah, hold on, Bohr radius. Depending on how you want to interpret things, some may say the electron actually could exist at the far ends of the universe, so to speak, because it's an extraordinarily low probability, and at some points it seems to be inside the proton. That seems kind of weird. So again, these are just numbers that exist that people have used for different calculations. So again, this is, again, even when I dropped off the 4/3 pi and everything, the closest that I could see was the proton at this. It just seems kind of odd that why the heck should the thing that we believe to be the Higgs, or something that seems to have properties of the Higgs at this particular mass, energy, and associated Compton wavelength, imploring just the concept of the spherical cow, or literally dividing it by a sphere, just with the Higgs-Compton wavelength as a radius. And it seems to give the magnitude of the cosmological constant. What the heck is going on? So I looked at this. I played around at least. Hold on, I'm sorry. Let me get back to the chat. I apologize. Oh God, so much stuff. I'm sorry. Let me get back here. 1 spherical cow, 2 spherical cows. Nerdy's commenting, the ideal things go completely outside the farm. Well, you gotta be careful outside the farm, Nerdy. There's like wolves and stuff out there. You don't know what might get you. It's easier to just kind of stay on the farm, just kind of migrate with the herd. You're less likely to get attacked. I mean, unless you're like a glutton for chaos or something. I mean, who would enjoy chaos? All right. Crypto is encouraging engagement. I'm not going to say no to that. Hey, I mean, I ain't your dad or anything. You interact with this video however you would like. Again, I ain't the boss of anybody. So, yes, all the stuff's some person. All the stuff. Invert the cow. Well, that's starting to get... We might show that animation of the inversion of a sphere, because apparently that's something you could kind of try to do. It still boggles my mind, and I'm wondering how that might work. And there it is, postulating. What if we started with perfect spheres and asked, what asymmetry complexities would we need to add back to make this actually work? It's... the cosmological constant is a B. Now, you might be referring to this guy over here. This is literally just mass energy of Higgs, so you could do something like... it's literally... Yeah, you could just write it as MHO C squared, MH0, M sub H0, your C squared there. You could just have it all as that. And you just have H naught, Compton wavelength, and then that. So, I mean, you could put it on a t-shirt. Technically, you don't need all this other stuff. Wolfram Alpha just happens to have that. So a noob like me can keep track of what the heck I'm actually talking about. And it's literally just... I was expecting, oh, okay, if there was something there, maybe you see a proportionality, like, maybe like the speed of light or something like that, or some factor or something like this. I was not expecting. Okay, why might this be the case? Let me, we'll get to that. It's well, yeah, it does give a really, really big number, because without that number, you get like 10 to the 42. Yeah, 10 to the 42 energy density or something like that. And I try to compare it to the Planck pressure. We can do that because the Planck pressure is maximal energy density, or technically, maybe momentum density might be a better way to say it. There's certain caveats there, so just pressure. So I figured maybe I would see something like this. I didn't see anything before that I noticed. I'm like, all right, it's kind of close to about, oh, actually, that's like 10 to the 70. So let's multiply that by the Planck length squared, because that's within about 1 magnitude there. So let's Planck length squared, because inverse Planck length squared is about, oh, Planck length squared is about 10 to the minus 70. So at least it might get us kind of close over there. Let me see. There we go. What the oh, yes. Oh, yeah, I broke that. Don't mind me. That side. Maybe if I actually zoom out so I can see what the heck I'm doing. All right. Now Planck length squared. Okay. Oh, that seems. Huh. Okay. 25 meters squared. So I'm gonna go on a hunch here. I'm assuming that Wolfram Alpha is rounding here, because obviously it must be. There's something else here, but I'm gonna make an educated guess, folks, from going down so many Wolfram holes. We're gonna divide it by 8 pi. Why? Because 8 pi, okay, again, we put some more data in there. It's a little less than 1 square meter. Oh. I did not look at this. Like I literally came across this the other day and then started. I look at things, I look at interesting things. I look at it a bunch of ways, and then I get very ADD and get drawn off into something else, because there's a couple more things that I would like to talk about relating to the Higgs and the weak sector. Then again, speculation, assumptions. Maybe it might be telling us something, but we're gonna have to save that for another day. The reason why I was doing that was because, well, number one, 8 pi is in that term there. Now, why there's probably some dimensional thing, but just hold on. 8 pi, it's a little over 25. If you were just rounding, it's 25. So, and it's also another factor in there. So again, if I get something that looks like something else, maybe the dimensions are off. Okay, is it a particular? Could it be telling us something? So I'm looking at dimensionless ratios from stuff that we know there. Okay, I did not know any of this stuff right here until just now. That's interesting. I have no idea. That's just sheer speculation. Why the heck should it come out to be about 1 meter squared? I mean, at that point, one might have to. Okay, here's the weird thing, and the thing that gets my noggin a jogging. I look at this stuff and I'm like, I'll play around with a toy model where I'm literally inserting 1 meter squared. Where I'm literally, or like meters. So I'm literally inserting meter, and for the model, scaling massive universe, so to speak, by the ratio between the meter and the Planck length. And I square that value. So basically, that squared Planck value, I multiply by that mass, so it gives you that ginormous number. Okay. I'm inserting a meter. I'm going to be honest about that one. Am I going to pretend like I'm not inserting something? That's an assumption. I didn't insert a meter anywhere here. So, like, that's why, and again, I'm very biased on this. I am so extremely biased on this. I have to be honest about that, because otherwise it's like, then you're just being shady. When it comes out to be about 1 meter squared, and that's a conversion factor or a factor that seems to line up when I make that assumption to a number of things, the difference between like the Planck spring constant and the mass energy of universe using that calculation. That's a crazy thing to say. The difference between them is 1 meter squared. I see this here and I'm like, it's not exactly 1 meter squared. It's got some, and again, we don't necessarily know, but I'm like, when I see this, I'm like, I would love to just randomly speculate and be like, oh, this must be. The long story short is, I'm sorry, I apologize about my rambling, is for some of these calculations, if you look at it, one might have to almost, in order to bolster them or say that there's any significance to them, you'd have to say that the meter is meaningful. What, are you kidding me? The meter is literally, it was originally defined as, was it the distance between the North Pole to the equator by way of Paris, because that's obviously how we do things, because that's where we also stored the kilogram for a while there, divided by like 1 million. Why? Because we were trying to take a factor of the Earth and everything. That should have nothing to do with it. Now, you could make the argument, the meter is now based upon the speed of light. Okay. But, the speed of light, but technically it is based upon the speed of light. Basically, the distance the speed of light goes in one second. So you can make those arguments there. But isn't that just our human convention? Now maybe you could say, well, it's the reference length. And I've done that before. And I can say that, and that's true. But is that actually significant? And I try to think about this, like, why should, at that point, you'd have to almost say, like, we got something incredibly right with our parameterization of reality. Like, if we had it that the meter actually truly meant something, rather than just an arbitrary thing, how could this be? I've gone through the exercise, and I'm thinking, I'm like, well, why would this be the case? At first, I'm like, the most substantive case I tried to make was, well, the Planck momentum is of order magnitude 1. Like, we exist in the realm of Planck momentum. That's about, basically, if you hit a baseball, it's got about the Planck momentum. It's a lot. It's, if you had something like the Planck mass, so basically like a mote of dust, and it was going at the speed of light, it would hit you with basically the momentum of a baseball getting like whacked by like probably close to a home run. Yeah, you probably feel that. The other thing, and this is something that's out there. It's something that I learned from doing my units project at the Wolfram Summer School. It's also something that mad scientist Rick DeWitt pointed out is the kilogram was originally based upon the mass of water. Or basically, I think it was about a deciliter of water. And even the conventional definition is if you take 1 cubic meter of water, it's basically going to be about 1,000 kilograms. A little, not quite, but hypothetically, if we were to have maybe like a pinch of salt, or there is and should exist a particular temperature and density, I think it's a little bit under the sea level pressure of Earth, like a little bit under the surface, there should be a cubic meter of water that equals exactly 1,000 kilograms. That was one of the original definitions for the kilogram. Now, that is out there because at that point, now it's like, all right, rather than saying our reference there means something, you're saying that the reference density of water is meaningful? I mean, that just seems bizarre. I mean, water is a fascinating thing, but. And just because the sun is a little over the density of water, that doesn't mean. I mean, that would be crazy because at that point, you're almost going to make a claim like some fundamental constant of nature is referencing water. It's like water hasn't even been created yet. So, I'm sorry, that was a really out there speculation. I have no idea. I mean, that would be awesome. Sorry for milking the. Yes, utterly massive. Yes. Yes, it has become cheese. It's maybe it's the Higgs Swiss condensate or something like that. I don't know. If you put some cheese in the microwave. Well, to be fair, the cosmic microwave background does have little perturbations and density fluctuations that is believed to be caused by dark matter, maybe some neutrino background or something. What if it? Oh, well, some person is now going into the complete. Okay, here's the thing. We're going into like the cosmic creamery hypothesis now because I was told a long time ago by at least someone, maybe it was like Looney Tunes or something, that the moon was obviously made of cheese. Well, if it was made of cheese, why haven't we been back in so long? So I feel like that might be disproving something unless there's something they're not telling us. So some Grey's Anatomy. The means go sour. The cream is still tasty with pierogies. Hey, Jax. Oh no, it's exactly. Yes, just like that. Oh, Jax, I did actually download Minicam when I did have before my Pornhub account got taken down because reused content and stuff. I guess they didn't like me that much. But okay. Let's get back to before I was going on the complete rant and everything. So let's go back. That was interesting. I have no idea. It's probably worth investigating further, but the long story is what happens if we take that spherical cow analogy seriously. So let's reiterate real quick. So, what happens if we take our Spherical God Cow? Okay, it's got a nice little Ultra Instinct aura around it, because that's what I asked ChatGPT to do for me. And we got that little equation over here, where basically we're just taking the mass of the Higgs boson, just its general mass, times the speed of light, so we're just taking the mass energy of the Higgs boson, or something that appears to be what many people at least believe to be the only elementary scalar spin zero particle of reality as we know it. Okay. So we're taking that mass energy. We are dividing it by a sphere, aka literally the spherical cow, doing a 4/3 pi r cubed. What R would we use? We're just using the Compton wavelength of the Higgs particle because we're taking its mass energy here. All right. Gives us a ginormous number. And what I was not expecting at all was when you divide that by the universe vacuum energy density, you get that like 1.1 times 10 to the minus 52. Which, okay, that shouldn't mean anything to anybody. But that does at least appear to be the dimensionless magnitude of the cosmological constant. Okay. So there's a difference of basically like 1 over meters squared. So I'm looking at this, and again, you could do this. You could literally divide it by, but now you're double dipping. So, because if you throw this all in here, and oh, let's go back. All right, let's do universe, vacuum, energy, density, blah blah blah. It took me a long time to figure out the precise incantation to actually get it to return things correctly. So I mean, to be fair, if you wanted to just double dip here, because the cosmological constant has that factor of universe energy density into it. So you're kind of double dipping if we want to divide it by that. Because when you divide it by that, you're just going to get out... why is it not showing? $10,000 square centimeters. That's... Why is it not showing the... Yeah, it's 1 meter squared. Okay, let's get into actually what's going on here. Full disclosure, do I know what's going on? No. It just seems to be a very interesting coincidence, so the long story short is we go back to the cosmological constant. I'm like, all right, so if we've already incorporated the vacuum energy density, and it seems to be the scalar of that, well, obviously, it must be this, that 8 pi g c4, because what is that? It's the Einstein kappa constant. No, it normally has c squared convention. We're using hold on. Maybe just Einstein kappa. C4 convention. We want the speed of light to the fourth because, well, we appear to live in 4 dimensions. It's our 3 dimensions are space plus 1 dimension of time. That seems to be pretty important. Okay. So long story short, what are we doing here? Oh my god. Einstein kappa constant. C4 convention. Okay, C2, C4. Here we go. All right, now there we are. Because if we look at this, it was like 2 times 10 to the minus 43. All right. We delete this. What is this? That's about 5 times 10 to the 42. Wait a second. That's a really big number. Well, this is a really small number. What if we combine them? Let's just do the naive thing. Let's multiply it by the Einstein constant. And again, we want our Einstein C4 convention. Well, it appears to balance at about 1 over meter squared. You end up getting the dimensionality of the cosmological constant, which is inverse meters squared. Technically just 1 over meter squared, you're dividing it by an area. Why the heck should it be 1? It's just something with our convention or something? And again, it's about 1. It's probably like, as we saw before, like 0.98. Then again, when we were putting in the cosmological constant there, Wolfram Alpha only lists it to like 2 decimal places, like 1.1. If you do this calculation out with more recent measurements of the Higgs and you calculate quantum wavelength and stuff, the actual magnitude is like 1.083, I think, times 10 to the minus 52. So it's a little there. If you're going to round, maybe there's a factor of like, I don't know, like square root of pi divided by 3 or something like that. I don't know. Again, more precision and knowledge about what's going on is there. It's just, I thought this was a kind of cool thing because it literally is the Spherical Cow exercise. We got some input for mass. Okay, it's reported at 125 GeV, and then they do the C squared to get the mass out. So I'm like, let's just report it in its energy state. Let's divide it by literally a spherical cow, just using our R for radius, whatever that is. Just as the Higgs associate Compton wavelength, we just cube that. So just standard 4/3 pi r cubed. Divide that into that energy, we get an energy density, and that energy density, when multiplied by the Einstein kappa C4 constant, so that's that whole 8 pi big G divided by C4, so it's just 8 pi divided by the Planck force, seems to give us about of magnitude 1 in the assigned units. I thought it was cool. And again, I'm not saying part of this is just, I hear folks say it's like, well, people have worked on this before, and it's like people looked at this, but there are issues and stuff, and it's like, it's just the most naive thing possible. I'm like, and again, I'm sure there's plenty of reasons why this doesn't make sense or doesn't work. It's just, I think it's kind of cool when occasionally you get something that seems to be about order 1, or if it's within 2 pi or something like that. Again, I'm just exploiting the resource. Now, you don't need Wolfram Alpha for this. You could just do all the hand calculations, which I'm sure my friend Casey would totally be for. And I'm not going to hate against this because, again, right here, it's saying 1, it's totally rounding. It is rounding there because it's probably like 0.9 or something like there. So to claim that it's precisely 1 with this, and again, this only put in probably maybe 3 digits. Wolfram Alpha has like 5 if we actually just go to like the Higgs. So it's just like Higgs particle should have like 125.18. Yeah, 125.18 GeV divided by C squared based on theoretical and experimental information. And again, it's telling you right there. That's why it usually just puts in 125, which seems to be about the magnitude. It's been measured a little bit below that. It's been measured to, I think, about 126.5 for earlier measurements by both, I think, or at least about 126 just by, I think, Atlas and CMS at one point or another. And then they seem to be honing in on somewhere around here, maybe a little bit higher. I just thought it was really cool that it was very close there, and you don't need to do this. It's just with a tool like Wolfram Alpha that basically is it's a calculator, but it also has an extremely vast, curated database, because a lot of folks that work for Team Wolfram, they've actually like studied and like are actual like physicists, mathematicians, programmers, and stuff. So like they have interest in these things. So you go out there, you update it a little bit here, a little bit there, and then you be honest, be like, this is based on theoretical and experimental information. And then I think they have the database somewhere and everything, but it's just, I can literally just type in words, and at least for just a quick level approximation, again, you want to go deeper with these things to see exactly what it would be. And again, from what I can tell is, who knows if the cosmological constant's even a thing? Because the weird thing about this whole, let's go back to the cosmological constant. So if we go back, cosmological constant. All right, we got this thing here. Yeah, it gives you that crazy number there. What happens if you take the square root of that? That's the reason I'm showing you this, because it's like, I could come up with whatever fancy equation, and even if it was as simple as possible, if potentially there's stuff going on that we're not aware of, maybe it's just an observational effect. Because when I do this, it's like, wait, into the minus 26 meters. We invert that. So we're going from 10 to the 26 inverse meters to about 10 to the 26 meters. Why do I say perhaps it might be an observational effect? Because it's basically the large height. It's basically of magnitude what the observable universe is. Now, the diameter of the observable universe. Okay. Well, I don't know. What if we multiply it by 2 pi? So just like your standard wavelength. 6 times 226 meters. It's it's not quite. It's pretty close to the diameter of the observable universe. Are we just is this just an effect from our observation based upon how far we're looking? I have to ask that question, and maybe I'm sure people have already answered this. I just don't have the answer right now. I'm just looking at this. I'm like, oh, here's some interesting relationships. And again, it's like, it's not some brilliant stroke of genius or something like that. It's like, if anything, it's like, I'm not a physicist, I'm not a mathematician, I'm a gamer. If you get a game, any game, if you get a fighting game, what's the first thing you do? Down quarter circle to forward punch. Why? You're trying to do a Hadouken. Or, I don't know, shoot a Sub-Zero freezing blast or something like that. Because a quarter circle rotation incorporating a button press, usually you'll perform a move. So I just look at stuff, I'm like, oh, this is cool. And since I'm such a noob and basically don't have all the background, I manipulated this. I'm like, all right, c squared, divide by c squared, 1 over this. And I have like a semi-videographic memory, so it's like, I'm pretty good at remembering like the first couple of significant digits and approximate exponential power to certain things if I see them enough. So that's why I just look at that. I'm like, that shouldn't be there. So again, it's speculation, and you're going to need to have a much more well thought out, logical, preferably rigorous, maybe to at least a physicist level of rigor. I mean, you would prefer more rigor because it's mathematicians and physicists. Sometimes it's kind of seems like, was it beans and cornbread had a fight? Something like that. It's exactly. Hadouken, my friends. Jax is commenting. Without games, there would be no human. I don't know if I'm not sure if my comment touches on metaphysical, because it's like, well, all we can really say is kind of like physical-ish stuff. But I have heard Stephen Wolfram occasionally say, it's like, let's say we were in a video game like played by the gods or something like that. Is that the case? Or are we just, I don't know, the Flatlanders in a game of Sims? We're actually just existing on some cosmic horizon, and this appears to be some 3+1 projection of stuff. I think Bill from Gravity for the Masses, he would tend to agree with that. It's like, I don't know. I try to entertain a bunch of ideas because I don't have the answer. I just look at things and I try to ask folks a whole bunch of questions so I can learn more to try to figure out what's actually going on. All right. Where are we? Oh, so much speculation here, so it's... I just think this was... Let's go into this paper, because this is... I looked real quick with some keywords, again, just casual Google. It was like cosmological constant, Higgs, and I think like Compton wavelength or something. So this is from R.J. Cosins. All right. So that we propose the relation of the mass of the Higgs is equal to the mass of the cosmological constant, and then some mass I, the square root of that. So they're taking a geometric mean, which I only skimmed this paper. I haven't delved deeply into it. I should probably do that the other day and actually email them. With the mass of the Higgs and the mass of the cosmological MI, denote the mass scale associated with the Higgs boson, the cosmological constant, and the inflaton, respectively. Okay, so it looks like they're trying to couple it to inflation, which I've heard people trying to do. This is just this was the one paper on the archive that at least I saw, and again, I didn't look all across the internet and all these. I just did the basic thing, saw what came up, and this was the thing that seemed to be closest to it. Because I think this person noticed kind of the same magnitude relationship they're coming at this from, I believe, a string field theory theoretic perspective. So they go into this. We got Alice Bob and everything like that. But let me link this here. I gotta put it in the comments below. So if anybody's interested in some more stuff here, this is a link to the paper, and there's a lot of interesting stuff. And I can now actually look at this and kind of try to start to parse what might actually be going on, because I'm like, all right, H bar C, so something about the bending stiffness of space. That seems pretty cool. And then they got some length lambda there. And again, it's they're doing some string tension for string theory. I don't care. First, the crazy thing is, I'll come across things that I'm looking for that are related. And again, I'm looking for patterns. But some of the things I come across, it's like, oh, we're assuming some 5-dimensional brain theory or something. And it's like some derivation of string theory. It's like, why would I discount it? Because you can complain all you want about string theory. The one thing you can't say about it is that it isn't rigorous. So that's why. And again, is this actually the way that things are? I don't know. But they go through a bunch of calculations here, and I do think they have some assumptions there. But again, the different interesting things is they got the Hubble constant here, and this is, I think, from like 7 years ago or something like that. This was oh, actually no, this is less than a year ago. Cool. So they have more recent information. So the interesting thing is the Hubble in seconds. It's oh, they had that like 2.2 times. Yeah, 10 to the minus 18 seconds. Oh, that's inverse seconds. So that. Hold on, Hubble constant? Why am I confusing myself? Hubble constant. I thought it was seconds, or is it inverse seconds? Oh, per second. Okay. But if it's per second, doesn't that make it a frequency? Oh, look, it does. 2.2 times 10 to the minus 18 hertz. Don't mind me. Higgs Compton wavelength. Just curious. Okay. I mean, that just... Oh, hold on. Compton frequency, because we can calculate that too. Hold on. Higgs boson Compton frequency. Oh, maybe I need to bracket this. I'm asking something that doesn't get asked very often, I think. Oh well, we'll look at it. I just noticed that it was about 4 away from the Compton wavelength of the Higgs boson. So it's basically those range of the weak force. It's like about 10 to the minus 17. Let's see. It comes out to be about 9.9 something times 10 to the minus 18. So Higgs. We'll do that later. It's all right. All right, let's see, where are we at? All right. Where are we? Okay, that's about all. So we went over the stuff. We spent an hour just chatting and ranting about that, and I gotta pull out the random poster of the Winged Dragon of Ra to just play upon that whole Egyptian god thingy there. So it's Just you gotta amalgamate, you gotta make things fun, because if things aren't fun, it's like, who cares? Now again, maybe you should care, but that's about all I got. I'm going over to my friend Jedi. Oh, I think he's got a stream. Maybe we'll redirect or something over there. Let's see. Can we get there? It's we're doing a stream on Godzilla Final Wars. So I think that's what we got going on. So I gotta get in there. Go to my own channel. Click on the stuff. But this is basically just a very scatterbrained preview of I think we got our next monastery conference coming up first week in November, so in about 2 weeks. I'm probably just gonna give a talk, much more well organized, talking about this, and should have this explored more deeply, so I can actually have something to, I don't know, maybe actually say about this rather than, oh, here are some words, here's some relationship that's a coincidence there, and maybe actually dive a little deeper, because it's like, what I'd love to just be like, oh, look, meter squared there, therefore this toy model must be with a way thing. No, that's not science. That's just rampant speculation with what, 2 digits of accuracy, if even? Come on. I mean, it's fun. It's fun. It's an interesting thing. It's just, I'm curious. Like, somebody had to have tried this before. Like, even if we didn't have all this data, even like 2013 or 2012 when we were measuring the Higgs, it's like this seems to be a Higgs thing about 126ish GeV. It's, again, would it be a bit off and everything? Sure, but it's like, even in 2013, there were things around estimating the Higgs mass at recent measurements that seem to have kind of, I don't know. What can you do? Just gotta keep on grinding it out, I guess. So let's see. Let's go to, we're at a live stream. I swear I can learn how to be a professional YouTuber someday. Options, blah, blah, blah. Oh, God, what is this doing? Details, blah, blah, blah. Doing live control. Oh, my God, no, not in the control room. I have no idea. Oh, hold on. Customization, audio library. I swear I'll learn someday. Languages. Community, analytics, dashboard. Oh, God. Why am I so bad? WrestleMania. Okay. Okay, let's just go to live control room. Stream hell. Oh, my God. It's telling me things. Oh. Oh, it's kind of like a Twitch studio there. I can kind of see it. Okay, see, I'm very slowly learning. All right, we go to that thing. Oh God. All right, I'm not gonna bore you all. Frequency. Okay, thanks, Bill. It's yeah, that's the thing. It's, I'm just looking at relationships that very often I look at something, I'm like, oh, that's kind of cool. And then you find it's like, all right, somebody did that 40 years ago. And it's like, maybe there's a no-go theorem. And again, I'm just assuming that I'm naive, that I don't have any special knowledge or anything like that. I'm just a monkey with a magic typewriter looking for, I don't know, somewhere to play. But okay, here we go. All right. Channel, creator, promotions, upload, defaults, general. Oh my God, there's so many things that I haven't looked at in so long. How do we, oh my God, I don't know how to do a dang thing here. Let's see. Well, I'm not gonna bore you all. I totally forgot how to do this. Let me go into it. And then, oh wait, is this here? Show more. And settings, standard. Oh my God. Why am I so dang bad at forgetting how to just do the next up thing? Oh wait, is it this guy? Customization. Oh. Redirect. Derp. I'm so freaking stupid. God cow. The Spherical God Cow. Oh, wait. Oh, it's not from videos. Wait a second. Redirect. Video. Live reactions. Stream customization. Why is this reader allow you to keep viewers across multiple events? Okay, I don't know how to do this. So my apologies. I'll take a look at some of the other things there. But yeah, that's all we got right now. So should be coming back with some other things that we may have higher confidence on that might even get weirder. And again, speculation. I put out things out there. Hopefully somebody might find something useful, and maybe we can figure out what's actually going on. Figure out high temperature superconductors. Figure out actual scalable fusion, and maybe actually have like a true post-scarcity society. If we can have abundant energy beyond all the different stuff and things, I think we solve a lot of these problems. I think most folks are good people, and I think there's a lot of really smart folks out there that might have some ideas that maybe we haven't heard much about yet, or perhaps certain ideas that may be starting to catch on. But other than that, we'll see. So thank you all for watching. Peace out, everybody. Take care of yourselves. And it's a crazy world out there.